Ngalakin kadijan yunga boja.
Hello, welcome to today's module. We will now discuss linear and time-invariant systems. Hopefully you've had a chance to look at the module where we describe and introduce systems, where we defined the importance of systems being causal and stable. Now we'll talk about a specific class of systems which are very important in engineering, and the most common systems we look at first, and in this unit only, are what we call linear and time-invariant systems. The usefulness of these systems is that the mathematical abstraction and modeling is a lot more simpler than systems which are nonlinear or time-varying. However, the price you pay with these nice simple systems that we will look at is that most practical systems these days, especially electronic systems using components like diodes and amplifiers, tend to be nonlinear, and most useful applications tend to be time-varying. But as I like to say, you have to walk before you run. It's best to look at linear time-invariant systems that we will do in this unit to get a feel for systems analysis and design. And when you need to later on, in later years, you can learn about how to handle nonlinear and time-varying systems. Obviously, they require a bit more analysis and processing, but at the end of the day, one of the techniques that I've seen used for those more elaborate systems is to simplify them to linear time-invariant operational regions. So in a sense, linear time-invariant systems, or considering a system to operate as a linear time-invariant system, is important to do any form of analysis and design. So let's look at what these linear time-invariant systems are all about. Now, going to the notes. We begin the discussion with section 146, where we define the concept of linearity. Now, you may have seen this in other units, and I think maybe in the circuits unit, you do cover the property of additivity, homogeneity, which together will give you the so-called superposition property. Here we define it in a purely systems context. So for this, we need at least two inputs. And of course, you can generalize it to 3 or 4 or more inputs, but we just look at 2 inputs to do the basic analysis. That is sufficient to tell us if a system is linear or not. So let's say we apply to a system an input 1 and input 2. For example, in our case, input 1 and input 2 would probably be 2 different inputs. Usually they're not the same input at different times because that's a different property. So x1 is a different input to x2. So far, we've looked at systems that you only look at one input, but you can have more than one input applied to a system. So you can apply, for example, in a circuit, you can have 2 voltages being applied to the circuit. You have one voltage source applying a current, applying a voltage of, say, 5 volts, and you have a second source applying a voltage of 7 volts. So x1 would be one of those voltage sources, x2 would be the other voltage source. And these 2 voltage sources could be applied one circuit with one voltage source, then the same circuit has that voltage source replaced by a second voltage source, or as we will see here, where both voltage sources are added together into the system. And that's where linearity comes in. So what we do is we actually consider if you have one of those inputs, it generates an output y1. The other input, x2, generates an output y2. What happens if the same system has an input equal to the sum of x1 and x2? Now, literally, that is the sum. So if you have a voltage input, one voltage was an input of 5, and the other voltage was an input of 7, the sum would, of course, be the voltage of 12. Now, this assumes you have a voltage signal, which is constant 5, constant 7. These could be time domain signals. So this could be a sinusoidal signal. This could be a triangular or square wave signal that we've defined previously, and this could be the sum of a sinusoidal signal and the square wave signal. A fairly complicated looking signal, I agree. But if it's a linear system, what you can do is, or you can say is, that when you apply this, say, sinusoidal signal with a square wave signal, the sum of the output that you see is, in fact, the sum of what happens if you only inject a sinusoid plus what would happen if you only inject the square wave. In other words, it's a linear system. it obeys additivity. It's not linear yet. We need two properties to be linear. So the first property is additivity. The response to a sum of inputs is the sum of the input responses. I think I better use my nice highlight tool. It looks a bit more visible. So the sum of the inputs is the sum of the input responses. Homogeneity is the property where if you take any input x and you scale it, multiply by a parameter alpha, and then you apply that input to the system, then the system response is such that it's the same response you would see if you had just the input x, and system response is scaled by the same factor alpha. In other words, our response to scaled input is the same scaled input response. So if alpha is equal to 2, you double the amplitude of the input, you will actually double the amplitude of the corresponding output. That is what homogeneity is. The superposition property, which leads us to it being a linear system, is the two operate together. So if you have this is the input, this has to be the output for a linear system. If this is not satisfied, the system is not linear. So how do you identify a linear system? Well, really the only way you can do that is to actually show that this holds, which means you need to have a mathematical definition of the system for which you can carry out this calculation. In practice, what we know is that elements like resistors, capacitors, and inductors which are known as passive elements, will generate or create a linear system. So all those passive circuits you would have looked at, circuits consisting of a combination of resistors, capacitors, and inductors, will in fact be a linear system. However, if any element consists of a rectifier, which effectively converts anything negative to positive, i.e. it's an absolute value of the input, or a square operation, that can happen. These are called squares, takes the input squared, or even what we call a compression operation, which applies a log function. These systems which tend to rectify or amplify in a non-linear in terms of the effect depends on the input value itself. You notice that the effect depends on the input value itself. These will be non-linear systems. The best way to highlight that is to look at the simplest one here, which is the square operation. So let's prove or disprove that this is not a linear system, and you'll see what we mean by that. Okay, I'll share my OneNote screen. So this is a bit complicated. I've never actually done this in usual lectures because it takes a bit of time to write it out on my OneNote. So that's the operation. If y is equal to tx, you could say that t is the square operation. I'll just represent it by that, where the input is squared. Let's see if I'm trying to think how I should define this. If you have an input x1 and x2, the best way is to create another input. So let's call it x3. That makes sense. Let's do this. There you go. And yes, I'm using A, not alpha. It's easy for me just to write A. Now, what we know is that what we can say is this: y1 of t will equal x1 squared of t. In other words, if the input is x1, here, this is the input, you just square it to get the output. Similarly, y2 will equal x2 squared. That makes sense. So if the input you apply is x1, this is the output. If the input you apply is x2, this is the output. The question is, what is the input if you apply x3? x3 is the sum of x1, x2 multiplied by a1, a2. Now, I have a problem here trying to flip easily between my OneNote and my lecture notes. I haven't set it up to do that, but if you go back to your lecture notes, you'll see that this is what we need to look at. So what is the response to this? Well, the response, of course, must be this. But we need to now relate that back to x1 and x2. So we actually have to square this whole thing. And that's where it gets a bit messy. Oops. Okay, what we will see is the following. Not something, you would have seen this before. It's not something that's just totally new. And this is the usual behavior when you square something like this. You will get the x1 squared term, the x2 squared term, and you get what's called the cross product term, this one here. And that is what y3 is. Now I will go back to the notes because you probably, the next step may not make sense if you forgot what we were trying to do. So let's just briefly change over, go to my notes, and remind ourselves what we're trying to do. What we've done now is we've calculated this part. That was the y3, that long, complicated expression. We need to show that it's equal to that. You can probably guess, just by remembering what I've done, that we're going to have a problem, and you'll see what the problem is. So we need to show what A1 plus, what does that equal? Well, that will equal this. Okay, now I'll need to shrink this a bit. That's a good thing about OneNote. I can shrink things so you can see everything. So this is equal to this. Okay, so if I can do this correctly, this is the output. That is this one here. That is the output when the input is A1 x1 plus A2. I think I'm missing. That's what I mean when I feel like I'm stressed by the edge of this notepad, notebook. Okay, x2t. So that's what you have here. This is just equal to that, obviously, because y1 is equal to x1 squared, y2 is equal to 2 squared. These are not the same. No way. In fact, they're really different. If they're not the same, the system is not linear. They have to be the same. This has to be equal to that in order for it to be linear. So x squared is obviously not linear if you think about the concept of linearity, because the gain depends on x. And in other words, if you think of it this way, perhaps another way to view it simply is to view it as this operation, where this is the gain, and this is the input. So that's the input, that's the gain. That gain depends on the input. A linear system shouldn't be like that. It shouldn't have gains which depend on the input, because the input, this gain will then depend on the input, and if the input is equal to x1 plus x2, the gain is different. So that's an issue. So you can probably realize that linear systems are highly simplified, but very elegant, because it allows us to do exactly what we see here. It allows us to consider the analysis and design of a system for one input, because it's easy to do, and then you can easily extend it for multiple inputs because of this property here, because the behavior is predictable. So if you design it to handle a sinusoidal input, then you know what it's going to do when you have a square wave input, because it's the same system, behaves the same, and you just add the two outputs together. So it behaves this way for a sinusoid, behaves this way for a square wave, and then you can tell what's going to behave if you add a square wave with a sinusoid. It makes the analysis and design quite simple. Now we move on to time varying and time invariant. And this is the one that I think still creates some angst amongst students and myself at times. The conceptual definition is actually very, very simple. And I think it's It's presented here. So let me see if I can highlight the conceptual one. And then I'll probably confuse you by looking at the more formal approach, but you probably get a better appreciation of the concept. The concept is this: the system does not change its behavior with time. That is about as simple as you can say it. A time invariant system, its behavior does not change with time. It's a grammatically correct statement, but for an engineer, it's a very vague statement. Engineers don't, what do you mean by behavior? Change in what way? So it's a bit vague, and so what we need to do now is actually define a bit more concretely, concisely, what this actually means. For practical purposes, if once we understand what it means, this is why it works so well. Analysis of a system is simplified by setting, say, t equal to a convenient value, like 0. That's very convenient. Analyze what happens to the system at time equals 0, and then that response will be the same for the system, for how the system will respond for the signal at any other time, because of this. If a system is time invariant, this is how it behaves. In other words, the system response at a delayed or shift for a shifted version of the input is the same as the response of the system to that input also shifted. So you work out the response of the system to this input at t equals 0, and then you take that same input and you shift it to another time, and you simply take that same response of the system at t equals 0 and shift it by the same time. That's it. A time varying system, however, is a lot more complicated. That one, if you shift it, if you present the input at a different time, the response will be different again. In other words, and I mean really different. The shape will be different, and that's what we need to now sort of describe. I'll do it on my OneNote for this system here, which which, as we will see, is not time invariant. So let's look at how we represent it as not time invariant, and also to understand what this actually means. Don't forget, the same also applies for discrete time systems. And of course, I forgot, this also applies for discrete time systems. Sometimes it becomes easy to just keep things simple. Here you notice I've not used t, and that's why, because it has to apply for both this continuous time and discrete time. However, in the example that I just showed, I'll only look at continuous time. Similarly here, I'm only going to look at continuous time. All these behaviors, linear, time varying, apply to discrete time as well. So let's go to my OneNote. Let's look at time varying now. I'll decide to be a bit creative and actually do it both mathematically and by a signal. And the signal one is more visual, and you can actually see what's happening. And I found this to be very, very useful for me as well. So let's start off with the system. That's what the system is. I'll create a nice simple input. The simpler the better, but not too simple. So this is a nice simple input. I think it's a rectangular wave, if I remember correctly. That's what it is. That's your input. Let's consider what happens when you shift it by, we need to look at time shift. So let's delay the input by 3 seconds. It would look like this. Okay, so it's delayed by 3 seconds. What would be the output for these two systems? Okay, so let's look at this one. So this would be yt equal to t xt. What would be the output? You can do it, but you realize, oh, okay, what's it actually doing? It makes you think about what the system is doing. The gain is t. So in other words, the gain here would be 0, so you get 0. The gain here would be 1 of 1, so you get 1. Here you get -1. I actually sketched the one I sketched was actually wrong. I hope I'm going to get this right now. It should look like that, shouldn't it? Yeah. Okay, I had a slightly different sketch when I did this before. So I hope now I'm not going to be Oh, this will be interesting. It's gonna let's check if that's correct. So t equals 0 gives you 0. T equals 1 means the gain is 1, and the gain is going to be 1 times a signal which has a value of 1. And here the t is -1. The value of x at -1 is 1, so you get -1 times 1 is -1. And you can probably guess it's going to be a straight line. So that's what you have. Now, what's going to happen here? Whoa, okay. This is going to be a bit more intriguing. So I'm not, now what yt is equal to, I'm going to leave open. And I need to shrink this so you can see. So what we'll do now is purely consider the waveform. So this is the waveform, and this is the function. So t must, of course, be that, I think. That's I interpret it as that, right? So this, ignore it's t minus 3. Just think of this as a, I don't know, another waveform. So this would be that, zt. It makes it a lot simpler to consider. So in that case, you would have 2, 3, and 4, and you'd be multiplying this 1 by 2, 3, and 4. So in a sense, it's going to go like that, where that's 2 and that's 4. And it's a bit squashed, so it's not to scale because this is 1, this is -1. So all you've delayed, you've actually just delayed that to here, and you get that. Wow, that versus that. These waveforms are completely different. You've just taken the input and shifted it by a bit, and you've got a completely different looking waveform. You can probably guess the behavior of the system is definitely not the same. It's definitely changed. So this is definitely not time varying. Now, let's look exactly how you show that mathematically. So the question is, what we need to figure out is what this looks like. Mathematically, what does that mean? Mathematically, this, what you see up here, which is this one here, is equal to this. This is what's happened. Can you see that? So think about it. Is it true that this, when you do this, you get that? Now I need to squeeze it more because you can't see all of it. Okay. So for example, let's say that's 2. So that's 2 there. 2 minus 3 is -1. -1, so you get 1. So it's 2 times 1 gives you 2. Put that 4 there. That's a 4 there. 4 minus 3 is 1. So you read off 1. It's 1. You get 4. Same 3. So that's it. So the system response is equal to that. However, if you look at what this looks like, this one here, then if that's yt minus 3, surely that will equal this. And in fact, that's what this is. Think about it. If you plug in 1 minus 3 is that right? 1 minus 3 is -2. I have to come back now. Let's see. T minus, you've delayed this by 3. Oh, sorry, I'm looking at the wrong one. Actually, no. I forgot something. Yes, I haven't sketched that one yet. sorry. What this is in fact, I knew it's the diagram. What this is, this is a tricky bit. So this is for 2. What you would expect to see is this. In other words, if the system was time varying, this is what you would see when this one goes in, this should come out if it was time invariant. Because it's time varying, you get that. So this is that. So that makes sense. 2 minus 3 is -1. 2 minus 3 is -1. -1 was 1. 1 times -1, you get -1. In fact, this is the same calculation as that because you just all the numbers just, once you plug in 2, 3, 4, you're effectively getting -1, 0, 1, the same effect. So you notice A time invariant system will actually take the same output, see here, and simply shift it. That's exactly what we expect for a time invariant system. It doesn't matter whether you apply the input there or there, you get the same output shifted. So this one would give you that. This one should give you that if it was time invariant. It is not, because this input instead gives you that. So this is not time invariant. Okay, sorry about the glitch. This is what happens when you're doing things and you don't do any post-production. I'm not going to try to edit that glitch out, but it sort of makes me appreciate it. Even I get tripped up, and hopefully I've not confused you. So let's go back and just remind ourselves what we have just done by going back to the notes. We've just shown, as identified here, we've just shown that when we shift the input for this one, we effectively get that coming out. And that's what we draw on my OneNote, that waveform that didn't look anything like the original, where you had tau equal to 3. So that was t x t minus 3. This, however, gives you this, which would be what we had in our case was for tau 3 was t minus 3 x t minus 3. So the trick here is how you make use of that, because you're not going to always be sketching things. And in an exam test, you really want to quickly figure out whether a system is time invariant or not. So this is the handy hint. And you can probably see this here and in our example. This is the easy one. This simply means that you take whatever you have here and simply, wherever you see t, you replace it by t minus tau. This is exactly what we've done here. This one's a bit different. This means that you only replace the input with t minus tau. So you replace that with t minus tau, but not that. Remember that. This one means only the input is delayed. All the other t's, anything else depending on time, does not get delayed, because that is part of the system. So the t here is part of the system. It is not affected, but the t here is the input, and that gets shifted. If you remember that, then you can do this analysis with any system that you may get, and you can quickly work out if it's time varying or time invariant. And the way to see that is these two have to be equal if it's time invariant. If they're not, it's time varying. So remember, for a system to be time invariant, its behavior must not change in time. Now, if a system is time invariant and linear, we have what we call a, obviously, linear time invariant system. So common and so useful is that we simply use the acronym LTI. And from now on, whenever you see the acronym LTI in these notes and even textbooks, it means linear time invariant system. Okay, folks, that's all for today. Thank you for listening in.